Ladies and gentlemen, Soft and Way Incorporated presents an overview of axial compressor conceptual design and analysis in AxSTREAM 3. Part 2. Compressor analysis and multi-point calculations. Analysis in AxSTREAM. The design phase is followed by analysis phase. Analysis provides the final performance estimation for any machine designed in AxSTREAM. The analysis task in AxSTREAM is performed with Direct Solver, which is a central part of the AxSTREAM suite. The Direct Solver is intended to solve the so-named direct task of turbomachinery, which is using known geometry to estimate machine performance. Direct Solver includes number of layers. Kernel layer solves a system of 4 classic equations: energy, continuity, process, and state. Middle tier layer is machine specific. It runs calculations dependent on type of turbomachinery. The outermost layers includes loss and fluid models. AxSTREAM provides a number of industry-proofed loss models suitable for subsonic and supersonic conditions. Loss models may be selectively associated with flow path components. AxSTREAM allows using embedded models for such standard fluids as water, steam, dry air, natural gas, and custom fluids. Custom fluids are defined with text tables. Precious models for specific fluids and mixes can be built using advanced property libraries, such as NistraProp library and others. Loss and fluid models exist as dynamic libraries. Such architecture allows the users to easily add new models or custom make new ones. AxSTREAM Direct Solver capabilities. Due to proprietary effective realization, AxSTREAM Direct Solver is able to find a solution for flow paths with up to 100 components, that is 50 stages, and up to 50 span-wise streamlines. AxSTREAM Direct Solver runs in 2 main modes: meanline mode and streamline mode. In meanline mode, solver estimate performance using meanline geometry only. The output data is extrapolated on other span-wise sections according to free vortex law. In streamline mode, solver takes into account the actual span-wise geometry distribution and output data is calculated for each span-wise streamline. For through-flow solutions, the solver uses streamline curvature method. This is why the direct solver is also often named as streamline solver. AxSTREAM Direct Streamline Solver is able to solve the different formulations of direct task. Those formulations are: calculate mass flow rate for given inlet outlet pressure. This formulation is the most general, and may be used with subsonic and supersonic cases also. Calculate outlet pressure for given mass flow rate and inlet pressure. This formulation is applicable for subsonic cases. AxSTREAM Direct Solver can be used via different interfaces. The main of it is Direct Solver Launcher. Launcher allows to specify boundary conditions, and monitor integral results: power, efficiency, mass flow rate, pressure ratio. Charts panes embedded in launcher frame shows the streamwise and span-wise distribution of main parameters. It may be blade and flow angle distribution, velocities, Mach numbers distribution, loss, diffusion factor distribution, work and flow coefficients, reaction distribution, velocity triangles, and so on. Direct Solver Advanced Capabilities. AxSTREAM Suite provides a number of advanced options related to Direct Solver. These options are: parametrical blade twist, blade vanes restaggering, simulation of different types of side streams, intercooling simulation, compressor maps calculation. Parametrical blade twist. Exit blade angle for long blades, as a rule vary along blade height. This blade twist is used to provide required cascade kinematics. AxSTREAM provides parametrical definition of blade twist. Exit blade angle distribution is defined with single parameter named twist factor. Exit angle distribution is defined with regards to mean section. This means that exit angle on meanline is constant. Twist parameterization allows run studies and optimization with multi-point calculation tools AxPlan and AxMap. Blade vane restaggering. The restaggering is a commonly used method to control compressor performance. Vanes and in some cases blades are rotated around their radial axes to decrease diffusion and avoid early stall appearance. AxSTREAM provides 3 options for restaggering simulation. Fixed restaggering rotation angle value is constant. This option may be used for ray rating calculations and retrofitting cases. Proportional restaggering rotation angles are defined as a ratio of restagger of first stator inlet guide vane. Proportional restaggering is widely used for industrial compressors. Restaggering by schedule. This option is used for aviation and aeroderivative compressors. AxSTREAM provides full-scale restaggering simulation including not only blade angle recalculation, but 3D model modification with respect to restagger. This allows to export restaggered 3D model for CFD simulation. The type of restaggering is selected in compressor table. For proportional restaggering the nominal restagger angle is defined. Actually it is a restagger of inlet guide vane. The raised use restagger flag means that this component will be restaggered with a selected ratio to nominal restaggered angle. Restaggering by schedule require restaggering charts. AxSTREAM provides an utility chart editor to create and maintain restaggering charts. Charts editor allow to create restagger schedule as a family of charts. Charts presents the distribution of restagger angle versus shaft rotation speed. Each chart relates to particular stator. Charts are stored in project, but can be saved in external file for use in other projects. When restagger schedule is connected to project, particular charts becomes available for association with stators. Side stream simulation. AxSTREAM allows to simulate different types of side streams. Fixed flow rate extractions injection. Pressure control extraction. Recycling. Fixed flow rate side stream. This type is used when it is necessary to change mass flow rate downstream side stream for predefined value. Pressure control extraction. Mass flow rate is defined with valve slot area, loss in valve, and valve back pressure. This side stream type can be used for surge valve simulation. Recycling extraction. This type of side stream suggests that extracted fluid will be returned to flow path upstream of extraction point. Mass flow rate E is defined with extraction slot area, loss in extraction tract, and pressure in injection point. Heat exchanger simulation. AxSTREAM provides special flow path component, heat exchanger. It is simulated with model of unlimited power, where outlet temperature of work fluid depends on coolant agent temperature and cooling coefficient sigma. There is a sample of using heat exchanger in compressor flow path. Heat exchanger is inserted after 6th stage. Pressure loss factor, heat exchange ratio, and coolant temperature are defined in exchanger property table. Calculation results present static temperature streamwise distribution. Mollier diagram shows the effects of fluid cooling. Supplemental analysis tools. AxSTREAM provides charts and tables tools for project analysis. Charts tool enables to present the distribution of any flow path parameter as a streamwise or spanwise distribution. Tables tool enables to present the project data in a form of custom-defined tables. AxSTREAM charts. Charts interface provide tools for charts properties, scope, and appearance selection. Properties to be displayed, as a chart is selected in project tree pane. Scope option selects and what part of flow path will be displayed. It may be machine whole flow path, module, stage or component. Appearance option allows to display charts in streamwise direction, that is along flow path, or in spanwise mode, along blade length. Also, charts allows to display experiment data and control its appearance. AxSTREAM tables. Tables tool allows to display tables for custom selected project objects. Tables as a charts are under the scope control. Tables may be used for data editing too. Displayed data may be copy-pasted to Excel spreadsheets. Table settings may be saved in profile file and later restored. It may be a number of profiles. Experiment option. AxSTREAM provides an experiment option to store and compare calculation results with external experimental data or other calculation run. Experiment option allows to save calculation results or test data in special project objects, parallel to main objects. Data saved in experiment structures can be displayed with charts and tables along with calculation results. An experiment can be created from AxSTREAM main project or flowcharts or tables modules. All created experiments are listed in project. Parallel data structures for calculation results are created with any new experiment. Charts display experiment data according to current display settings. Experimental curves displays automatically when appropriate property is selected to display. Filter control the appearance of charts for specific objects inlet, outlet, hub, tip, mean, etc. The presentation of experiment curves on charts is controlled experiment settings. Show hide control appearance experiment data on charts and tables. The line color, type and weight, marker shape can be changed here also. Custom report tool. AxSTREAM provides an option to prepare formatted custom reports for selected components. Report can be customized from topmost components up to profiles coordinates. Different groups of properties may be included or excluded from reports. Reports can be created in RTF and HTML formats, with contents and page breaks. The contents of custom report is controlled via tree-like view of project structure. Project tree allows to select any project object with its derivatives and select formatting options. The first page of custom report includes general data stored in project. There are project information and project notes. Report contents is formatted as outline list. The data of all objects included in custom report are printed as a table. The data of all objects included in custom report are printed as a table. Multi-point calculations in AxSTREAM. Multi-point calculations are used to explore the correlations between some operational or geometrical parameters and turbine performance. AxSTREAM provides two multi-point calculation tools. Those are Map Generator Tool, AxMap. Design of Experiment Study Tool, AxPlan. Both of them use AxSTREAM Direct Solver as an engine. Map Generation Tool AxMap. AxMap is an effective tool to generate compressor maps, and study the influence of operational parameters on compressor performance. As a multi-point analysis tool, AxMap runs a series of direct task calculations for two variables and a number of additional parameters. In compressor design and analysis, AxMap is used for automatic calculation of different performance curves. AxMap Setup. Due to tight integration, the map setup study is easy and transparent. Design variables and objective functions are taken immediately from the studied project, and depend on type of task, to be solved with Direct Solver. To set up a map, user has to select required objectives, variables, and parameters. Objective selection. Any calculated AxSTREAM project data item may be used as an objective. The objectives are listed as correspondent items are located in AxSTREAM project structure. The selected objectives are shown in Map Objective table. Variables and parameter selection. AxMap variables are selected among AxSTREAM project parameters that have any noticeable influence on compressor performance. Mapped variables are listed tree-like project structure. The selected variables and parameters are shown in Mapped Variable table. AxMap can use two main variables and a number of parameters. AxMap performs calculations in series. The values of one of main variable defines the series, that is columns of map matrix. Other main variable defines points of series, that is rows of map matrix. For each of variable a range of its value variation has been specified too. The parameters are supplemental to series variable. The value of parameters can be specified for each series. Map detailed setup. Map detailed setup allows to set up each map series. The value of column variable may be specified for each series. This is important for compressor maps, where each series is calculated for certain rotation speed. Parameters are supplemental to series variable. Parameters values may be specified for each series. By default, row values are evenly distributed between minimal and maximal values. Additional parameter control distribution gradient. If it is required, the values of row parameters may be set manually. Some series columns may be declared as constant. They are not calculated, but are open to input data manually or with copy-paste. Constant columns are used to present external test data. Map calculation results. Each row in map calculation results corresponds to particular map point calculation. It includes values of used variables and parameters and values of specified objectives. Calculation results table allow to recalculate particular point, or save some point in main project. Maps presentation. For map presentation, AxMap do not make difference between variables and objectives. Despite the mass flow rate is an objective, AxMap shows curves of outlet pressure versus mass flow rate. The displayed map presents validation calculations of NASA Stage 37. Blue curves presents AxSTREAM calculation results and red, experimental data from NASA report. AxMap can overlap calculated curves with those built for other machine. This allows to compare calculated performance with experimental data. There is special option in AxMap, which allows to overlap turbine curves and compressor maps, necessary for turbine compressor matching. Design of experiment tool. AxPlan. AxPlan is an effective tool to study or optimize the flow path versus a number of parameters. Design of experiment methodology used in AxPlan allows to build smooth n-dimensional response surface, using a small numbers of direct solver runs. For each of two variables and any objectives, the result of AxPlan can be presented as 3D surface. AxPlan setup. An experiment plan setup uses two groups of data. The first group is a set of objectives necessary to be studied. Any calculated AxSTREAM project data item may be used as an objective. The objectives are listed in tree-like AxSTREAM project structure. The second group is a set of required variables. AxPlan variables are selected among AxSTREAM project parameters that have any noticeable influence on compressor performance. Plans variables are listed in tree-like AxSTREAM project structure too. For each of variable, a range of its value variation has been specified. AxPlan can use up to 20 variables. It runs direct solver calculations for a minimal number of specially selected combinations of variables values of points, and then builds mathematical models for objective functions. Blade twist optimization is one of most typical tasks solved with AxPlan. Pressure ratio, efficiency and mass flow rate are selected as objectives. First and second stage rotor's twist factor are selected as planned variables. This dose study will be performed using 9 runs of direct solver. After all 9 runs would be completed successfully, the resulting response surface is built automatically. Map view allows to see 2D diagrams. Efficiency and power in a space of stator and rotor twist factors are selected to display here. Efficiency contours pink ellipses shows that maximum of efficiency is inside explored range. 3D view of response surface gives yet more realistic presentation. One of variables here it is efficiency is displayed as 3D surface, and others as contours on this surface. The embedded random search engine allows the user to find the optimal solution on the response surface in a fraction of a second and with high precision. Please see part 3 for continue.